So wait, so can you just I guess restate what you just mentioned your question earlier, your research question. Can you restate
Mhm.
what that was again?
Yeah, so I actually didn't I don't think I ever said it because I was
I
trying
don't
to
think you
like
did.
Finny probably
give
cut you off or something.
Yeah, probably knowing me.
um but so what I am trying to figure out, and this is like the part of the research that definitely does not have an answer yet. A lot of like things like Catalan numbers and bijections, like there is a lot of work that's already been done on that, but this question doesn't have an answer yet. And it's basically given given like a set of triangulations of an n-gon of any magnitude,
Hmm.
let's require that this set, any two that you choose must share an edge. It doesn't have to be the same one, but like if you have like I don't know, like 12 of them and you pick the first one and the ninth one, they have to have just one at least chord in common. And then you could pick a
Oh,
different
okay.
set of two, and those two have to have a chord in common. It doesn't have to be the same one. It could be, but it doesn't need to be. But the question is basically what is the upper bound of the size, like the cardinality of that set? Like how big, how many can you have that share this property? And I mean that's so like all of this work on like finding bijections and understanding like the patterns and like the properties of these triangulations and how these relate to Catalan numbers is like in an effort to try and make a statement about how big you can make that set.
Okay. So just to clarify, you have some n-gon, two-dimensional n-gon, right?
Yeah.
Um, and then you draw a bunch of chords that can't cross. Like you connect a bunch of vertices, draw a bunch of chord. Do they um like do these all have to end up being triangles basically?
Yes.
And then the like is the triangulation the set of all the triangles or the number of all the triangles? Like what is the
So
triangulation?
the triangulation is just so like say you have like a pentagon and you connect like the bottom vertex, the bottom right with the top one and the bottom left with the top one. That's a triangulation. That
Okay.
it's those like two
With
chords.
three triangles, right?
Yes.
Okay.
And so and the set of all possible triangulations of a pentagon, there's only five of them in total at all.
Right.
And those actually all of them, if you consider like all of them, any two can actually that's not true. But you can generate all of them from one. But that's a different question. But like the maximum number of different triangulations in a possible set, for instance, like for a pentagon, let's say you want to have um like if you consider just that chord, the first chord, like the one from like the bottom left up to
Yeah.
the top, there's
Mhm.
two triangulations that share that chord because you can draw the other line from the top to the other
Oh.
bottom one, or or you can draw the other chord. You see, like
Okay,
I think a visual would help, but like
so there's five different ways you can triangulate a pentagon, right?
yeah,
And like with like considering those five, there are some of those share common chords.
yeah,
So keep going with what you were saying. So what's
yeah.
the
So the question is like, how many can you put together such that any two of them share a common chord? So like,
oh, any two triangulations
yes, any two triangulations share a
share
common
at
chord.
least one common chord.
Yes. So like, for instance, you can create a
Oh.
set of two of those pentagonal triangulations where two of them share the same chord, and but you can also like if you go up a dimension, like if you are talking about a hexagon, you can create at least a set of five elements that uh, that share a common chord. And the reason for that is because of the recursive nature of the Catalan numbers. Because if you think about starting with one chord, then you've then you're just considering now a pentagon because you've basically lopped off one of the vertices. And we
Okay.
already know there's 5 ways to triangulate a pentagon. So now you have automatically 5 triangulations of a hexagon that necessarily share the same chord. But that's also subtly
Oh.
subtly that is a different question though, because
Yeah.
the question doesn't require that that chord be the same. So it's what I'm trying to like think about currently is whether or not requiring that that chord be the same actually gets you more in that set than if you like want there to be variation. Because I don't know, and this is because of like I haven't answered this question, so I don't know. But
It's what
once
you're
you
working on.
yeah, and once you go up a dimension again, it gets even higher. Like if you're considering like a heptagon and you like require that they all of your triangulations share the same edge, now you can have you can be certain that your set will have at least 14, in fact only 14 of triangulations because now you're considering a hexagon because you already know that one of those vertices has that edge right in front of it, and so you lop it off and now you're considering just the hexagon. Um and 14 seems to be in the very, very preliminary work that I've done on this, like kind of the largest set that I can make. So I don't know. But
And
yeah,
so
that's the
the
question.
goal is to sit like just so make sure I understand this. You want to find what is the maximum number of triangulations such that any two will share at least one common chord.
Yes.
Yeah.
Okay.
Can
Like
I
Very
can I
given
just
an
nice.
sorry,
n-gon or like because that's going to depend on like are you saying like given a specific shape? Like you
Yes.
okay.
So like you're given one
Sorry.
you're given an n-gon. The you're only going to consider triangulations of the that n-gon,
Okay.
but the goal is to generalize over
As a
n. So
function of
like
n.
yeah, as a function of some type of relation to yes.
Okay.
So because when you're working in low enough numbers, like working with like a pentagon or a hexagon, in theory, I could probably try to like look at all of them and just like pick out whatever the largest that I possibly could. But as soon as you even move up to 7, like 42 is already a lot to handle.
Yeah.
So
yeah.
the generalization is the goal. Yeah.
Can
Liam, what
I
were you
can I
So
saying?
just
you,
can I just
yeah, Liam.
clarify something real quick or not reclarify, I just ask is the triangulation, is that where you're connecting all the vertices through it? Like in a pentagon, I could make a W in it basically. Is that a triangulation, or a triangulation is just any single triangle that's made in it? I guess I missed
The
that.
triangulation basically there. So a general triangulation will have n minus 3 chords in it, like necessarily. You have
Okay.
to divide the shape into only triangles. Like you couldn't have just one chord in a pentagon and then leave the other 3 vertices untouched. Like you have to, or I guess the other two, you have to have a full triangulation for it to count.
And a
And so I
triangulation
just
is
think about
whenever
it.
you make a shape fully out of triangles.
Mhm.
Okay.
Wait, no, I just meant with the W. Like if I think about a pentagon, if you have one of the points on the top going down, if you make a W-ish shape, that'll split it into triangles. Are the 5 just that and then rotated 5 times? Is that what the 5
No,
are for a pentagon? No, is that
no,
am I
because
misunderstanding what you mean by that?
the pentagon will only have 2 internal chords in its triangulation because your n in that case is 5 if we're talking about n as in the number of vertices. So if you think about there is like a W style triangulation, but that includes 2 external edges if you're like trying to make that W. You don't really consider the external edges of the pentagon. You're only really thinking about the 2 in the middle, and those two you could have one that goes like horizontally across the pentagon, and then another one that comes from one of those vertices and then goes to one of the ones in the bottom corner. And that would be yeah, a rotation. But then when you move up a dimension, there are families of these triangulations that can't be translated into one another. So and that's kind of related to what I mentioned very briefly, but with dihedral groups, which is all about rotations and like rotations and reflections basically. But like, so if you think about like, say like a hexagon, kind of one of like the first triangulations you could think of is if you have like one vertex and then like you have three chords coming out of it and it goes to like the three opposite vertices and it makes a little like fan. As soon as you change one of those so that it's not all of them are like starting from that same corner vertex, there's no possible way to rotate or flip your starting triangulation into the other one because you've moved the orientation of that chord. But there is a set of 6 where if you do rotate, you will create different triangulations that are like in that basically like rotational family kind of is what I was actually working on this afternoon.
And can I just ask again, what did you mean external vertex when you said the pentagon? Like it has 5 vertices. How are they external?
So external
or not?
edges, like the external edges are like the ones that are like actually making the shape of the pentagon, and then the internal ones are the chords that will.
Oh, like, 1, 2 chords make it. Okay.
Yeah.
Interesting. Okay.
Because there's a lot of math you can do about like the number of chords in something like a connected graph, and that includes those external chords. But the triangulation is really only dependent on the internal chords rather than those external ones. And the degree of the vertices, which is the way to kind of the key to translating that bijection between parenthesis strings and triangulations is like vertex degree, which is like the number of edges coming out of it. That also only is concerned with the internal edges when you're talking about triangulations.
Okay,
just
so
dense.
All of us just like stopped talking. It was like we're all trying to figure out what
this is like. It would be. I promise you, like, and this is also kind of related to like the question of like mathematical education. The visual is so helpful.
Super important.
That's why Finian's going to be doing some animations for this.